Welcome to Cape Chemistry 2024, Module 2, Question 2. Let's go. 2A. What is meant by the term dynamic equilibrium? A system is in dynamic equilibrium when the rate of the forward reaction is equal to the rate of the backward reaction in a reversible reaction. 2. Part B. The reaction between A and B to form C and D is represented in the following equation. Here we have the equation A plus B with the reversible reaction sign to produce C plus D. Now the first thing I'm seeing here is that our state symbols are all in the liquid state. Now that is an issue because we cannot write equilibrium constant with liquids or solids. They must be in the gaseous or aqueous state. But let's see what the question is asking for. The equilibrium constant value for the reaction is 4.0. B part 1. Write an expression for the equilibrium constant of the reverse reaction. So this is where the issue is. Because it's pure liquid, it should not appear in the equilibrium expression. There should be no equilibrium constant for this equation because all the values are in the liquid state. However, if they're asking for a numerical value in part 2, then we're just going to write the equation. But please note that when we write the equilibrium constant for concentration, the state symbol must be in the aqueous or the gaseous state. We should not be able to write an equilibrium constant. However, based on what they're asking, they want to see an expression or an equation. So we'll just write that for their sake. Now for the forward reaction, the constant for Kc or the equilibrium constant for concentration Kc would be the product of the products divided by the products of the reactants. What I mean by that is the multiplication of the products divided by the multiplication of the reactants. And that value is 4. So if they want the reverse reaction, then you have to write AB being the product while CD being the reactant concentrations. So in that case, for the reverse reaction, this would be the correct equation if the state symbols were in the aqueous or the gaseous state. Now that would mean that C and D would be the reactant concentrations for the reverse reaction and A and B would be the product. So according to the definition of the constant, it is going to be the product of the products. So it's going to be the conc of A times the conc of B divided by the conc of C times the conc of D for the reverse reaction. So that would be our Kc equation. And that would now give us a value of 0.25. Because if in the forward reaction, the value is 4, the reverse reaction would be 1 over 4, which gives us a Kc value of 0.25. So for part 2, state the numerical value of the equilibrium constant for the reverse reaction based on the expression in B1, then our value would be 0.25. Let's continue. Part C, state Le Chatelier's principle. Now, if a system is in equilibrium and a change in temperature, pressure, or concentration occurs, the system will move in such a way to oppose the change to relieve that stress and restore a state of equilibrium. So whatever stress you put on the system will oppose a change. So if you increase pressure on the system will decrease pressure. If you increase temperature, the system will decrease temperature. If you increase concentration, the system will move in such a way to decrease the concentration and return to equilibrium. Part D. Consider the following equilibrium reactions. Here we have equilibrium A, and we have steam plus carbon in the solid state, the reversible reaction, H2 gas and carbon monoxide. And you can see that this reaction is an endothermic one. For equilibrium B, we have our aqueous chromate ion plus H plus ion, the reversible reaction to give you dichromate aqueous ion and water. Now use Le Chatelier's principle to predict and explain the effect of 1. Increasing the pressure on equilibrium A. Now the first thing I want to note is that we have gas as our state symbol here and solid. So the solid would not contribute to the pressure. Here we have 1 mole of steam on the left hand side, and we have 1 mole of H2 gas and 1 mole of carbon monoxide gas. So in total we have 2 moles of gases on the right hand side and 1 mole of gas on the left hand side. This means that the side with the lower number of moles would be the low pressure side, and the side with the higher pressure would be the side with the higher number of moles. Now you'll recall that pressure is directly proportional to number of moles. So that's important. So if we have on the right hand side the higher number of moles, it means that this is the side with the high pressure. And if you increase pressure on the system, according to Chatellier's principle, the system will oppose the change by decreasing the pressure, and it does so by shifting to the left or shifting to the side with a lower number of moles. So when you increase pressure on the system will decrease the pressure by shifting to the side with a fewer number of moles or the lower number of moles. So our answer should be the position of equilibrium will shift to the left where there are fewer gas molecules. And you can see that in the equation. Part 2, decreasing the temperature on equilibrium A. So again, if you look at the equation, you'll see that our enthalpy change is positive 131. This means that it is an endothermic reaction. So heat is a part of the reactants. Now if heat is a part of the reactants and you decrease the temperature, what you're doing is you are removing heat from the reactant side. Now the system will oppose that change. Because we are decreasing or removing heat, the system will put back the heat. So it will cause the system to shift to the left. So the position of equilibrium will shift to the left. Decreasing the temperature removes heat from the reactant side. This system will shift to the left to replenish or replace the heat, maintaining equilibrium. Part 3. Increasing the H plus aqueous concentration on equilibrium B. So here we're looking at this equilibrium here, and if you increase H plus concentration, the system will want to decrease what you are increasing. So the system will shift the position of equilibrium to the right to oppose a change of increasing the H plus concentration. And that would be your answer for part 2 and part 3. Part E. A buffer solution containing 0.2 mole per dm cube of a weak acid HA and 0.5 mole per dm cube of the sodium salt of a weak acid NaA was prepared for use in the food industry. E part 1. Define the term buffer solution. Buffer solution is a solution which resists pH changes when small amounts of an acid or alkali are added to it. E part 2. Given the Ka for the weak acid to be 7.4 times 10 to the minus 4 moles per dm cube, calculate the pH of the buffer solution. Now we can do it one of two ways. We can use the Henderson-Hasselbalch equation, where we know that pH is equal to pKa plus the log of the conjugate base concentration over the weak acid. So we can now plug in our values. Now pKa is equal to minus log Ka, and we have the Ka value here. So we just put that in our calculator to find the pKa value. Plus log of the conjugate base, which is 0.5, given in the question, because the conjugate base is a sodium salt, and the weak acid is 0.2. So pH is equal to pKa, which is 3.13, plus, when you find the log of the concentration of 0.5, divided by 0.2, you get 0.397. When you add those two values, the pH value works out to be 3.527. Now another way you could do it is to find the concentration from the acid dissociation constant. So Ka is now the concentration of the product of H plus times A minus, the conjugate base, divided by the concentration of the weak acid. We are then going to make the concentration of H plus the subject of the formula, and therefore H plus is now equal to Ka times the concentration of the weak acid over the concentration of the conjugate base. We're now going to plug in the values. The Ka value was given in the question, to be 7.4 times 10 to the minus 4 times the weak acid concentration divided by the conjugate base concentration, and that works out to be 2.96 times 10 to the minus 4. So this is the H plus concentration. Now to find the pH, pH is equal to minus log H plus concentration. So you plug in the calculator, minus log 2.96 times 10 to the minus 4. Therefore, pH is equal to 3.528, which is almost the same as what we calculated earlier. Let's continue. Part F. Outline the experimental procedure which can be used to prepare a sample of the buffer solution in E. Include in your answer test to be used to ensure a buffer solution was made. Okay, so let's run through the steps quickly. First thing we're going to do is transfer, using a burette, 25 cm cube of the 0.2 mole per dm cube of the weak acid into a beaker. Using another burette, we're going to add 25 cm cube of 0.5 mole per dm cube solution of the conjugate base, which is the sodium salt of the weak acid, and that will be added to the beaker. We're then going to find the pH of the mixture using a pH meter. To a 10 cm cube sample of the buffer solution in a test tube, we're going to add a drop of 2 mole per dm cube HCl and measure the pH. Remember, a buffer solution should resist changes in pH when small amounts of acids or alkali are added. So the pH should be pretty much constant. After that, to a 10 cm cube sample again of the buffer solution in a test tube, we're now going to add a drop of 2 mole per dm cube sodium hydroxide and measure the pH. Again, the pH should remain constant because it is a buffer solution, so it should resist changes in pH. Part G. With the aid of equations, explain how a solution of ammonium sulfate and ammonia can control pH. So a solution of ammonium sulfate and ammonia pretty much is a buffer solution, and therefore it should resist changes in pH. So in this case, the buffer solution is a mixture of ammonium ion and aqueous ammonia. So the ammonium ion is an ammonium salt. So it can be ammonium chloride, ammonium sulfate, any ammonium salt. And of course, aqueous ammonia is ammonium hydroxide. So this is our buffer solution or our buffer mixture. So we have a conjugate acid. The ammonium ion is the conjugate acid, and the aqueous ammonia is the base. Now, if you add small amounts of acid to the buffer solution, then the base should counteract it by reacting with it, forming something that was already present in your buffer solution. So you form ammonium ion that was present already, and therefore the pH should remain constant. So the base counteracts the H plus ions to produce ammonium ions, maintaining a constant pH. If you add small amounts of OH minus ions, then from the buffer solution, the conjugate acid would react with the base. And so we're going to form ammonium hydroxide, which is aqueous ammonia. So again, we're forming something that's already present in our solution, and that will maintain a constant pH. So for this part, the conjugate acid counteracts the alkali, the OH minus ions, to produce aqueous ammonia, maintaining a constant pH. So either of these equations could be written. So in this case, ammonium ion plus hydroxide ion produces aqueous ammonia and water. Or you could simply form ammonium hydroxide. Part H. Define the term half-life. Half-life is the time taken for the concentration of a reactant to move to half of its original concentration. Part I. Using a Boltzmann distribution curve, show how a catalyst affects the rate of a chemical reaction. So this is our Boltzmann distribution curve, where on the y-axis we have the number of particles with a certain amount of energy. On the x-axis we have energy. Now the question wants us to show how a catalyst affects the rate of a chemical reaction. So in the first instant, this line represents the activation energy without a catalyst. It means that all the particles below this line would not be able to form products without overcoming the energy here. So all the particles above this line reach the activation energy, therefore they can produce products. All the ones below, the energy is not sufficient to overcome the energy barrier. Now what a catalyst does, it lowers the energy barrier so that those particles that were not able to form products in the first instant are now able to form products because the activation energy was lowered. So now only these particles on this side of this line cannot produce products, but all the particles now on the right hand side have enough energy to produce product. In other words, the energy barrier was reached or overcome. And that's how a catalyst affects the rate of a chemical reaction. This is the end of Cape Chemistry Unit 1, Module 2, Question 2. Please remember to like, subscribe, and click the notification bell so that when new videos are uploaded, you will be notified. Thank you.